In this lesson, we will see how to tackle urban complexity using digital tools and integrated approaches. Cities are dynamic systems that require data and adaptive models in order to be improved. We will talk about urban diagnostics, real-time data from sensors, the Internet of Things, and the geographic information model. Predictive modeling with urban digital twins, urban retrofit, and adaptive monitoring. Useful tools for designing smarter, more sustainable, and more resilient cities. Cities are multidimensional dynamic systems composed of anthropic, functional, physical, and geomorphological elements characterized by an interconnected network of flows of energy, materials, information, and people. Their management is made complex by the interaction between these elements and by the unpredictability of the phenomena that characterize them. Unlike simple systems where a cause generates a predictable effect, in complex systems small changes can produce unforeseen and amplified consequences at different scales. This principle, known as nonlinearity, is particularly evident when analyzing phenomena such as the effects that climate change, population growth, and uncontrolled urbanization have on cities, which represent their most urgent challenges. These phenomena tend to manifest themselves in a non-gradual way, often with effects that are difficult to predict or manage. This is the case with climate change, which is not a linear phenomenon, but rather a set of interconnected processes that can lead to sudden and irreversible changes, something we have already experienced firsthand in our cities. In fact, climate change has caused rising temperatures and heat islands, meaning a progressive increase in temperatures that triggers cascading effects such as more frequent heat waves, water stress, higher energy consumption, and the deterioration of air quality. Extreme weather events, such as floods and hurricanes, are not only becoming more frequent, but are also occurring with increasing intensity, putting urban infrastructure under pressure and causing nonlinear economic and social damage. Loss of biodiversity and environmental degradation, changes that may seem gradual, can lead to a point of no return for urban ecosystems, with irreversible effects on the soil's absorption capacity and the regulation of the city's microclimate. The unpredictability of these complex phenomena makes resilient urban planning and management necessary, capable of adapting quickly and reducing risks through the use of climate data, predictive simulations, and mitigation tools. In this context, the digital transition provides advanced tools to analyze, monitor, modify, simulate, and optimize urban dynamics, improving quality of life and the resilience of territories. Without an approach based on reliable data and advanced analytical tools, there is a risk of making decisions that are ineffective or unsustainable in the long term. To address urban challenges, cities must be seen as dynamic and adaptive systems, not simply as collections of infrastructure and populations. This requires advanced tools based on data and technologies for more effective management and planning. To govern this complexity, it is essential to adopt a systemic approach that considers the connections between various urban sectors such as transportation, energy, environment, and economy. Understanding and monitoring urban conditions in real time, therefore, becomes essential. Thanks to the use of sensors, geospatial data, and advanced digital tools, it is possible to collect information on air quality, mobility flows, and energy consumption, thus obtaining a clear and up-to-date view of the city. To address this complexity, it is necessary to adopt a systemic vision that takes into account the interdependencies among the various urban subsystems: transportation, energy, environment, food, economy, and to monitor urban performance in real time by using sensors, geospatial data, and digital tools to collect information on air quality, mobility, and energy consumption. The use of big data and predictive models allows cities to shift from reactive management to proactive management, preventing critical issues before they fully manifest. Urban transformation must be supported by advanced tools that make it possible to assess the impact of decisions before they are implemented. This approach makes it possible to avoid costly mistakes and improve the quality of urban planning. Some key tools include urban modeling based on GIS, which allows for testing urban development strategies by identifying optimal solutions for the distribution of services and infrastructure. Urban digital twins offer the ability to simulate the behavior of cities in real time, testing scenarios such as population growth, sustainable mobility, and adaptation to climate change. Simulating the consequences of urban transformations makes it possible to identify more balanced solutions, ensuring greater sustainability. To manage complex and unpredictable urban phenomena, an integrated approach is essential that combines urban regulation, advanced diagnostics, and data-driven strategies. Digitalization offers comprehensive solutions to address complexity and improve sustainability. To manage urban complexity, it is necessary to combine data analysis with the ability to adapt to unforeseen changes. Cities must develop tools that allow them to integrate the structural dimension with urban performance in order to improve efficiency and quality of life, to anticipate and respond to unforeseen changes, energy crises, demographic shifts, and health emergencies, with flexible and scalable strategies, and to optimize available resources to ensure sustainable growth while avoiding waste and inefficiency. This requires the integration of specific tools and methods, such as those we use in our activities, which are based on the Integrated Modification Methodology, known as IMM. This methodology operates through urban diagnostics, that is, the use of advanced technologies such as sensors and the Internet of Things, which make it possible to collect real-time data on urban performance, mobility, environmental quality, and energy consumption. Geospatial analysis through GIS systems makes it possible to examine the structure of urban systems and relate it to their performance, thereby improving our ability to understand and predict outcomes. Simulation and predictive modeling, that is, the use of big data, predictive analytics, and urban digital twins models, allow us to test infrastructural solutions and urban strategies before they are implemented. This approach makes it possible to identify recurring patterns, evaluate alternative scenarios, optimize resource management, and prevent critical issues. Urban retrofit, meaning the optimization of solutions through iterative processes that refine interventions based on collected data and performed simulations, promotes adaptive and resilient solutions. Urban strategies cannot be effective without community involvement. The active contribution of citizens and stakeholders is essential to ensure sustainable and shared solutions. Some tools to encourage participation include e-governance platforms, as they allow citizens to express their opinions and contribute to urban planning, and co-design workshops, which are collaborative spaces where administrations, experts, and the community work together to define shared strategies. The adoption of these tools within a systemic approach makes it possible to transform cities into smarter, more resilient, and more inclusive ecosystems capable of effectively responding to the challenges of sustainability and digital transition. The digital transition is not just an opportunity, but a necessity to ensure quality of life, efficiency, and sustainability. Are we ready to embrace an innovative vision for the future of our cities?